Effect of the seismic wave direction on the collapse of RC box girder bridges. Abstract: the gradual collapse of ordinary structures due to gravity and blast loads is the subject of a significant number of research studies. The progressive collapse caused by seismic actions, especially of bridge structures, is being investigated by a few others. Some of the serious earthquakes in the past have resulted in significant damage or the collapse of bridge buildings, resulting in devastating losses. New analysis and monitoring methods for the damage process, from initial failure to final collapse and can follow the structural failure trend, have been built in order to construct new improved earthquake-resistant bridges. The current paper analyzes the behavior of bridge progressive collapse by serious seismic actions using the applied element approach AEM, which takes into account the separation of structural members or components, from failure to complete collapse, and falling contact debris or impact forces. A monolithic RC box girder bridge were numerically analyzed under the influence of Kobe seismic ground motion in longitudinal and transverse directions. The results showed that the effect of the seismic wave in the longitudinal direction of the bridge was more destructive than that in the transverse direction. Keywords: progressive collapse, applied element method, box girder, ground motion direction. 1. Introduction. Progressive collapse phenomenon is defined as the global damage or collapse behavior of a large part of the structural system that is caused by a failure of a relatively small or localized part of the structure. Structural progressive collapse occurs as a result of failure of one or more structural members or components. The load is transferred in the structural system due to changes in the distribution of stiffness, the pattern of the stress behavior, and / or the structural boundary conditions. Crothammer et al., 2002. This initial failure results in other structural elements being further overloaded and later fail. Studies on the progressive collapse of existing structures have focused primarily on high impact as in blasting or irregular loading. Not so much attention is paid to the vulnerability of structures, especially bridges, with regard to progressive collapse during earthquakes. Starosek 2006. Wibowo et al., 2009, studied the seismic progressive collapse of RC bridges during earthquakes. They modeled only a continuous bridge that was previously experimented with. Gudez, 1997. The results have shown a good agreement. The separation of structural components resulting from fracture failure and impact forces from falling debris had been taken into consideration. The results have shown a significant influence on the performance of bridges during major earthquakes that were visible in its progressive collapse analysis. These also demonstrate the need to include progressive failure mechanisms in the assessment of seismic design efficiency and bridge evaluation that would not only lead to a better and more robust earthquake-resistant design for new structures but also more efficient retrofitting and reinforcement strategies for older structures. In a similar vein, Salem et al., 2016, analyzed numerically the collapse of Tsuyagawa Bridge damaged by the Tohoku tsunami in March 2011. The Tohoku tsunami swept across Japan's eastern coast, killing over 15,000 people and missing over 2,500. The tsunami caused more than 400,000 buildings to collapse and more than 250 coastal bridges to be washed away. The analysis showed accurately the collapse behavior of the bridge, showing that the bridge collapsed at a water velocity of 6.6 m/s caused by its pier's flexural failure. Tsuyagawa Bridge's AEM analysis has shown the ability to simulate the 2011 Tohoku tsunami collapse effectively, although the analytical results showed less ductility when compared to reality. Domineski et al., 2020, analyzed numerically the collapse of the viaduct over the Polsvera Valley in Genoa that collapsed in August 2018. This incident left 43 deaths, and several injuries caused by a collapse of a portion of the highway connection. The results of the analysis showed that the stay cable was the most important item whose failure caused the collapse. Furthermore, the simulation model indicated that the main girder triggered the collapse and the large visible displacements involved in their collapse would have warned the authorities of the impending fault. 2. Applied element method. The Extreme Loading for Structures, ELS, program, developed by ACI 2018 is based on the AEM, which was initially developed by Tageldin and Maguro, 2000a, B, at the University of Tokyo in 1998 to solve problems related to two-dimensional plane stresses. It was later expanded to solve three-dimensional problems. The AEM is a novel method of modeling that adopts the discrete cracking concept in AEM. Structures are modeled as an element assembly. The elements are not rigid and connected by normal and shear springs along their joint surfaces. These springs are responsible for normal and shear stresses transfer between adjacent elements. Each spring represents a certain volume of material stresses and deformations. Once the connecting springs fail, each of the two adjacent elements can be completely separated. The AEM adopts fully nonlinear path-dependent material constitutive models. AEM is a stiffness-based approach in which an overall stiffness matrix is formulated and equilibrium equations for each of the stiffness, mass, and damping matrices for structural deformations, displacements and rotations, are nonlinearly solved. The equilibrium equation solution is an implicit one that takes step-by-step dynamic integration, Newmark beta time integration procedure, Bath 1995, Chopra 1995. If the springs connecting the elements are ruptured, two adjacent elements are separated from each other. Elements may separate, recontact, or contact other elements automatically depending on the structural response. 3 Material models. 3.1 Modeling concrete and reinforcing steel. Maikawa model is used to model concrete in compression, whereas for concrete in tension, the linear stress-strain relationship is adopted. In this stage, concrete is exposed to tension up to cracking where the stresses are set to zero afterward. Furthermore, for concrete in shear, a linear relationship between shear stresses and strain is assumed before the cracking. After cracking, a drop in the value of shear stresses to zero takes place. H. Okamura and M. Kohichi, 1991. Springs are also used to define the reinforcement between elements. Ristic model, Ristic, D. 1986, is used to model the reinforcement. Newmark SS approach is used to solve equations of dynamics. The equilibrium equations are indeed linear for each step and are generally solved, in AEM, by using a direct or an iterative solver. 3.2 Bridge bearing material. An interface material is used to model bearings. The interface material model is a pre-cracked element where the material is initially cracked and cannot bear tensile stresses. As for compression, the stress-strain relation is linear up to compression failure stress. The relationship between shear stress and shear strain is linear until the shear stress approaches Sn, coefficient of normal friction x normal stress. At this stress level, the shear stress remains the value, Sn, as long as there is no change in normal stresses. The compressive stress variation allows the proportional variation in shear stresses, Sn. The shear stiffness is set as a minimum, if the crack opens or during active sliding of the bearing. Salem et al., 2016. For comparison of AEM and FEM. During progressive collapse analysis, the failure, separation, contact, and falling debris of elements must be traced. Using FEM, it is very difficult to model progressive collapse. On the other hand, using AEM, to analyze these processes is made easy and effective taking into consideration all the analysis stages until collision, Fig. 1. 6 Bridge models. 6.1 Bridge layout. RC box girder bridge were modeled 3 spans with 2.5 m span, Fig. 2. The bridge superstructure is monolithic box girder with columns. The columns are assumed to be fixed at its bases. The bridge box girder is rested on 5 elastomeric bearings plates at the superstructure edges. The bridge dimensions and reinforcement details were originally taken from executed multi-span box girder bridges in Egypt. The reinforced concrete damping ratio is assumed 5% during the analysis. The analyzed bridge model and the reinforcement of the box girder is shown in Fig. 3, and Table 1. The purpose of analyzing models A1KL and A1KT is to determine the effect of severe seismic ground motions, like Kobe, on RC box girder when applied on longitudinal and transverse direction. 6.2 Material properties. The material properties adopted in AEM analysis are presented in Table 2. A full bond between the concrete and the reinforcing steel was assumed. The used bearing was composed of a top and bottom steel plates and bearing material in between as in Salem et al., 2016. The dimensions of the steel plates used were 500 x 500 x 50 mm. The dimension of the elastomeric bearing interface was assumed 350 x 350 x 130 mm, Akagol, C. and Selick, O. 2008. The interface between the steel plates was given bearing material properties, Salem et al., 2016. A relatively high compressive strength was given to the bearing interface so it could not fail in compression and act linearly, Chen, W.F., and Duan, L. 2014. The shear modulus of the bearing was assumed to be 2 MPa, Malek S. 2007, and Ken Akagol and Oga C. 2008. 7 Ground acceleration. Kobe, ground acceleration was used in the collapse analysis of the bridge models, as there was some bridge collapse during these earthquakes. Mitchell et al., 1995, Anderson et al., 1996, Kawashima, 2000, Wallace, et al., 2001, and HSU and FU, 2004. The ground motions data was obtained from the Pacific Earthquake Engineering Research, PEER, Strong Motion Database, PEER, 2019. A summary of the earthquake ground motions used in this research is presented in Table 3 and is shown in Fig 4. The time used in the seismic analysis was reduced to the time that contains the largest cycles of seismic accelerations to reduce the ELS analysis time, as the time that would not contain significant values of acceleration could be omitted. The used time step during the analysis was 0.004. Earthquake analysis usually requires, of 0.001 to 0.01 second when a collision is expected to occur. The smaller the time step, the higher the accuracy and the convergence of results becomes. 8. Mesh sensitivity analysis. A mesh sensitivity analysis was carried out to obtain a suitable mesh size that would be used in all the analysis cases for columns and bridge superstructure. Horizontal and vertical concentrated loads were used for the column and the box girder respectively. Fig 5 shows the relationship between the mesh elements and the displacement of the column and the deflection of the box girder. 22 elements per column S height and 5x12 elements per column's cross-section were used. The maximum dimensions for the column's elements were 200x200 mm per element cross-section and was 38 cm per element height. Each surface area of the box girder, i.e., the deck, soffit, and webs, was divided into 5x1 elements with 50 elements per 25 m length, span, in the box girder's longitudinal direction. This mesh size was found to give accurate results. An analysis using a finer mesh has been carried out without any noticeable difference in the displacement and deformation. The total number of elements used was 10,000. The AEM mesh used was accurate enough during the elastic region and in the small deformation range of the inelastic region, Tageldin and Maguro, 2000a, b. 9. Analysis results. The analysis was carried out on two stages. The first was static to take into account the gravity loads and original deformations of the bridge, whereas the second was a dynamic analysis. 9.1 Reinforcement reduction effect. Fig 6 shows the displacement time history for the right column of A1ML, A1MT, and models. The two models showed a relatively identical displacement pattern until the 16th second, as the displacement of model A1ML increased due to the total collapse of the right and middle box girders. It is noted that model A1ML showed greater by double displacement than of model A1MT. The reason that the rigidity of the column in the longitudinal direction is lower than that in the transverse direction. Fig 7 shows the straining actions. The straining actions of A1ML, A1MT at the 8th second, the axial force of model A1ML is reduced by 50% as the right bay of the box girder collapsed. At the 21th second, after the collapse of the middle bay of the box, the axial force is nearly zero. At the 14th second, the axial force of model A1MT is reduced after the failure of the right bay of the box girder. It is also noted that the right column of model A1MT exhibited greater moment than model A1ML. 9.3 Collapse analysis of the different bridge models during Kobe ground motion. A comparison between models A1ML, A2MT, are presented in Figs 11, 12, respectively. At the end of the analysis time, A1ML and A2MT collapsed. Reinforcement reduction beyond the minimum reinforcement ratio, model A3MK according to the ECP 203-2007, allowed the bridge model to show a collapse behavior. At failure initiation after 4 seconds, the webs of the box girder showed excessive cracks. At 7.25 seconds, the web of the right box girder failed mainly in shear. At 8 seconds, the right bay of the box girder hit the ground. At the 15th second, the left box girder initiated failure in shear and settled on the ground. At analysis termination reaching the 20th second, the middle bay failed and the bay weight dragged the left column down. Contrary to expected, by changing the ground motion direction from longitudinal to transverse direction, model A1MT showed a less collapse pattern as the right bay of the box girder is the only collapsed part of the bridge model. 10. Conclusion. In the current study, the seismic progressive collapse behavior and analysis of reinforced concrete bridges were analyzed. Various bridge configurations, monolithic with columns, continuous on bearings, simple on bearings bridge models were analyzed. The bridge models and selected earthquake excitations used in the study were discussed. A summary of the findings is presented herein. ELS program can be a means to predict the behavior of ordinary and special structures against abnormal events during the design, construction, and service loads. Bridges can be analyzed with respect to the direction of the ground motion, obtaining the collapse pattern, and analyzing the necessary strengthening to prevent the possibility of collapse using ELS program. Contrary to expected, the effect of the seismic ground motions in longitudinal direction is more destructive than its effect in the transverse direction. Conflict of interest statement. On behalf of all authors, the corresponding author states that there is no conflict of interest. Data availability statement. The datasets used to defend the findings of this study are incorporated into the article.